Welcome back. I'm sorry for the bad circumstances. I wish we could meet in person. We'll have to do these video lectures instead. What I'm going to do to try and speed things up, because I know these are really boring, is write up the notes ahead of time and then present them at double speed, so you get sort of half the time it usually takes me to present each section, because I won't have to write it all down as I go. And what you can do, though, is with the video, then you can rewind and play it over and over. It'll probably take as long after that. But we'll do some video lectures since we can't meet in person. Today's topic will be improper integrals. And I think you'll find this one pretty fun because it tells you how to evaluate integrals with infinities in them. One of the fascinating things that comes out of this is that some infinitely long regions actually have finite area. That's the big result that comes out of this, and we can prove it. Suppose a definite integral has an infinite interval of integration. All right, goes out forever like this. Or maybe it integrates a function that goes in both directions, plus or minus infinity, or integrates a function that has an asymptote and it goes up to plus or minus infinity somewhere in the middle of the interval. These areas might still be finite, and we're going to try and evaluate them with what's called an improper integral, since it doesn't go between constant endpoints and have the function remain continuous. So an improper integral can be one of these kinds of forms. It can be an integral from a to infinity, an infinite endpoint of a function. So it's trying to find essentially the area under the curve forever. It can be an integral from minus infinity to b, a fixed point, an integral to the left forever. Or it can be an integral in both directions forever, minus infinity to infinity. Or it can be an integral from a to b, where the function goes up towards an asymptote or down towards an asymptote, or both. And we'll make these definitions. For the first case, how would it do that? Well, we could, if I stopped at any finite point, I could go from a to b and evaluate that, right, for a nice function like a continuous function. And maybe I can make b a little bigger and take the area again. Make b a little bigger and take the area again. And if you think about it, if as b gets larger and larger going out to infinity, these areas out to b are settling down to a finite number. That ought to be what we call the area under here. It's the limit of the areas from a to b as b gets bigger and bigger going out to infinity. So we'll define it that way. Limit as b goes to infinity of integral from a to b of f of x dx that we do know how to calculate. Similarly, if we have an integral from minus infinity to infinity, we'll just integrate from a fixed point a to b, and then let a get smaller and smaller going to minus infinity. If this limit exists, then we'll say that's the value of this improper integral. And if we go out both directions, we can pick any intermediate point c we want whatsoever, integrate from a to c, take the limit as a goes back to minus infinity. Here's c, so we evaluate this area essentially. We integrate from that same point c out to b and let b go to infinity, so we're essentially adding these two problems here to evaluate the integral from minus infinity to infinity. Finally, if there's an infinite spot in the middle somewhere, we can integrate from a to b an interval that includes that by integrating from a to k, a number a little less than c, and taking the limit as k approaches c from the left. Integrate from another number k on the right to b, and take the limit as k goes to c from the right. You can think of this as c1 and c2. They're not the same c. This one c is a little less than k is a little less than c. This one k is a little greater than c. And you let them both come together, and you say this integral is the sum of these two limits of integrals. So that's how we'll define all those things. It just makes intuitive sense once you think about it a little bit. So suppose we want to define the area below this interesting curve. F of x equals 1 over x squared. We know how to sketch that from algebra, right? And we let the integration go from 1 out to infinity, so we want this area. Is that area finite, I wonder? Well, I say by our definition, it's the limit as b goes to infinity, integrating from 1 to a finite point b, 1 over x squared. Well, the integral of 1 over x squared is minus 1 over x, right? This is x to the minus 2. Its integral is minus 1x to the minus 1. And then we want to evaluate that 1 and b and take the limit as b goes to infinity. Well, you plug in b, you get minus 1 over b. Plug in 1, you get minus 1 over 1. And subtract them. Then you take the limit as b goes to infinity. Oh, this one approaches 0. This one minus 1 is 1. So this actually has unit area, area 1, under y equals 1 over x squared going from 1 to infinity. Kind of surprising maybe, huh? Here's another one. Suppose instead of trying to find the area under 1 over x squared, I try and find the area under 1 over x. That also shrinks down quickly. Maybe like this one, it'll shrink down so quickly that it will have a finite area, right? A limit of these areas as b gets bigger and bigger. So we try it. Integral 1 over x is the limit as b goes to infinity of 1 over x from 1 to b. Well, that's integral 1 over x is the natural logarithm, so this is ln b minus ln 1. ln 1 is 0, you recall from algebra. But wait a minute, as b goes to infinity, the limit of ln b is infinity. So this one is actually not dropping down towards the x-axis fast enough. As you go out here, these limits these areas going out to b get bigger and bigger, bigger than any number you want, no matter how large, so we say the limit is infinity. This points out something, too, for words to describe this. In this case, where you cannot have a finite value for the definite integral, we'll say the integral is convergent because the limit converges to a number. And if the integral gives you infinity, we'll say the integral is divergent. So those are terms for improper integrals. Here's an example evaluation of an improper integral. This time, with an infinity within the limits of integration, we go between finite endpoints, but look, on the left it goes up to infinity. So maybe this area is finite in here, maybe it's not. We evaluate this by taking the integral from a to 0, and then let a approach minus 1 and see what the limit is. That's the definition for an integral with an asymptote in it. So we take the limit as a approaches minus 1 from the right. The integral is arc sine, right? 1 over square root 1 minus arc squared is the derivative of arc sine. And then it has to go from a to 0. The a is cut off a little here. So we have limit as a approaches minus 1 from the right of arc sine 0 minus arc sine a. Well, that's minus arc sine of minus 1. You can just plug this in to evaluate arc sine, actually. Right? It's a continuous function. Its limit is equal to the value by plugging in. And you get, when you plug in the top endpoint, and the bottom endpoint, minus arc sine of minus 1, which comes out to be pi over 2. So, how do you get pi over 2 out of it? It's hard to imagine, but surprisingly, a lot of these integrals that you come up with turn out to have pi in them. And this is one of them that maybe you wouldn't have guessed. So this area is actually pi over 2. How about another one? Suppose I wanted to integrate from minus infinity to infinity, right? 1 over x squared plus 4. How can I do that? Remember on these things, the duck rule, if it looks like a duck, if it walks like a duck, it's probably a duck, right? That looks like 1 over x squared plus 1. That looks like an arctangent integral. How can I make it so, right? Well, I think if I let u equal 2x here, then I can rewrite this, x equals 2u. Then dx is going to be 2 du, just by taking the derivative multiplied by du. And I can first rewrite this as the improper integral from minus infinity to 0. Any intermediate point does it. I picked 0 because it's an easy point. So limit as a goes to minus infinity integral from a to 0 plus limit as b goes to infinity integral from 0 to b is the way you evaluate this integral from minus infinity to infinity. Break it up into 2 pieces. And now each of these needs the substitution. X equals 2u, dx equals 2 du. When I make that substitution, right, x squared becomes 4u squared. Dx becomes 2 du. And I have this integral, both of them are that way. And then you take the limit and this one is a goes to minus infinity, and then this one is b goes to plus infinity. Well, we can evaluate that by integrating here. Since I made up 1 over u squared plus 1, I recognize that integral is the arctangent of u. So I need the 1/2, the limit is a goes to minus infinity of the arctangent of u, plus 1/2 the limit of arctangent 1/2 b. Well, what are those limits? Is a goes to minus infinity of minus the arctangent, and the limit is b goes to infinity of plus the arctangent. We can do those pretty simply. I'll show you what the arctangent looks like. If I can put this up for a second. The arctangent function looks like this. The definition of limit, or of horizontal asymptote, says that the limit of this function, y equals arctangent, let's say, let's just say x, as x goes to infinity, is what? Since this gets closer and closer to the horizontal line, y equals pi over 2, we note that the limit as x goes to infinity of arctangent x is pi over 2. Similarly on this end, if we take the limit as x approaches minus infinity of arctangent of x, this is getting closer and closer to the line y equals minus pi over 2, so this limit is minus pi over 2. That's how I evaluated the limits on here. Limit is u goes to infinity of arctangent, minus infinity of arctangent u. We have to write this out in 2 steps. Arctangent 0 is 0, so you get 0 at the top end point and minus arctangent on the bottom, but then arctangent is evaluated at minus infinity, so you get minus a minus pi over 2 all times a half here. This one's, those double negatives are hard to follow, right? This one, no double negatives, right? Arctangent of a number as that number goes to infinity, 1/2 b as b goes to infinity. The arctangent is approaching that asymptote pi over 2. It's all multiplied by a half, and we've got 1/2 pi over 2. Here also, this integral marvelously, 1 over x squared plus 4 from minus infinity to infinity is pi. How about that? You never guessed there's exactly pi units under this curve, probably, right? Well, one important observation that comes out of this, you want to have a feeling for these. When are these going to converge? When are these going to diverge? Comes out of the following, essentially, theorem that I'm going to establish. The first 2 integrations we did, 1 over x and 1 over x squared, recall, from 1 to infinity, illustrate a very important concept. We can consider the more general problem of integral 1 over x to the p with respect to x from 1 to infinity. That, by our definition of the improper integral, is the limit as b goes to infinity of the integral from 1 to b, 1 over x to the p. We're only going to consider p positive. If p is negative, this thing is obviously infinite. The thing doesn't decline to the x-axis. Well, integral 1 over x to the p is integral x to the minus p, whose integral is x to the minus p plus 1 over minus p plus 1. Right? That's the antiderivative. And if p isn't equal to 1, that's what the integral is. However, if p equals 1, this is the integral 1 over x, and then you get natural logarithm. So this limit becomes one of these 2 limits. This one if p isn't 1, and this one if p is 1. What we observe then, this one, if p is between 0 and 1, this will be x to a positive exponent, and as b goes to infinity, x to a positive exponent, b to a positive exponent as b goes to infinity is going to give us infinity. So this one will be infinite if p is between 0 and 1. But if p is bigger than 1, then this comes as x to a negative power, and as b goes to infinity, x to a negative power approaches 0, so you get 0 for the top end point, and the bottom end point, plugging in 1, you just get 1 over p minus 1 over minus p plus 1 at the bottom end point, which is subtracted. So you subtract the bottom end point, that gives you 1 over minus p plus 1, you get 1 over p minus 1, minus this thing. And so if p is greater than 1, we observe this actually does have the limit of the top end point is 0, the limit of the bottom end point is 1 over minus p plus 1, gives you value of the integral 1 over p minus 1. There's the integral of 1 over x to the p. If p is greater than 1, it's 1 over p minus 1, a finite result. So depending on the value of p, you can get a convergent integral or a divergent integral. Now what if p equals 1? You take limit it as b go to infinity, ln b. ln of infinity is infinity, so this one is also divergent. So you get a divergent integral 1 over x to the p. If p is between 0 and 1, including 1, but a convergent integral if p is greater than 1, and that's the limiting case. The 1 over x integral is something to compare these other integrals with, to have some intuition whether an improper integral is going to be convergent and divergent. Look at this one. This one, as x gets very positive or very negative, looks mostly like 1 over x squared, right? The plus 4 has very little influence to a large number of digits, and so we say this looks like a 1 over x squared integral. P 1 over x squared is convergent, right? So we could have anticipated that this one would integrate. The first two cases we put up there were actually integrals 1 over x to the p with p equals 1 and 2, and sure enough we found it diverge for p equals 1, converge for p equals 2. So have this anticipation. If an integrand drops to 0 faster than 1 over x, you expect it to converge. If it drops to 0 slower, you expect it to diverge. I say faster, it has to go like 1 over x to the p plus epsilon, and then you can guarantee convergence by this theorem. Here's a fun example. This kind of makes an interesting case for improper integrals. This is called Gabriel's horn. It's a problem out of your book. And suppose I take the y equals 1 over x function that we already did, our second example, and we found out the area of this infinite strip is infinity, right? If you tried to paint that, you can't. It is infinite amount of paint to paint that. But now suppose we take this infinite strip and we twirl it around the x-axis like that and create a horn. Gabriel's horn, so Gabriel can stand off in heaven and blow the horn. Well, maybe Gabriel needs an infinite amount of volume to push a sound through here. It turns out he doesn't, because when it's revolved around here, remember the method of disks? The volume of the horn is pi f of x squared dx, where f of x is the radius, 1 over x. So if pi radius squared dx integrated from 1 to infinity gives us the volume of the infinite horn. But the integral 1 over x squared, recall, from 1 to infinity is 1, or 1 over p minus 1 by the formula 3, is 1. And Gabriel's horn actually has volume exactly pi. So he can blow a finite amount of volume from an infinite distance. And it leaves us with this apparent contradiction. How can we take a paper of infinite area, twirl it around, and get a finite volume? Seems like we could just stick that piece of paper into the tube here and paint it, right? It's a finite amount of paint in here. We can paint it with a finite amount of paint. How is it we say it takes an infinite amount of paint then, has an infinite area? There's a good question for you. Actually, there's a good answer. Maybe we'll talk about it next time.